Good morning. First of all, I would like to thank the organizer for the invitation. It's the first time that I come to India, and I really find this place impressive. So thank you very much. Thank you a lot. Then, okay, this was the original title and the original plan, but then I realized that I didn't have enough time to talk about everything. So this is the new title. So it's only generalized hydrodynamics and invariant subspaces. So I would like to start with an introduction on quench dynamics, although I think you already know, especially if you have been here the past week. So what we call the quench, quantum quench, is the time evolution after sudden change of a Hamiltonian parameter, as was coined by John Cardy 15 years ago or something, like, not 10, 15 years ago. Generally, the setup is that one prepared the initial state in the ground state of the Hamiltonian, then study the time evolution of after changing the parameter. And something which is important is generally one considers a many-body system. So many-body system that could be, for example, a spin lattice system or a quantum field theory. And this is very important. In this talk, I will focus on spin lattice systems. And I will, in particular, I will consider cases where the local dimension is finite, which can be, for example, the spin system. So there can be fermions, ER, spins, but not bosons, for example. And what is important is that the dimension of the Hilbert space, in this case, is scaled exponentially with the volume, okay, in the systems. Now, one of the reasons why we have been very interested in this kind of settings is about the relaxation in a quantum many-body system. And now you can see immediately that there is something a bit weird going on here, because I'm considering a spin lattice system, which is finite in a sense, and then I'm talking about relaxation, while we know that in quantum physics there is a theorem that prevents relaxation, which is the quantum recurrence theorem. Indeed, it was shown 70 years ago or more that you can always find a sufficiently large time such that the initial state, the state at that time is practically equal to the initial state. Okay? And so you can distinguish the two states using some observables. And in this paper, okay, they also were commented about the results by von Neumann, saying that the assumption of John von Neumann were kind of strict and it was difficult to realize in real systems. And moreover, okay, they also emphasized that even if you consider macroscopic observables, they will go back to their original values. So there is no real relaxation. So in order to speak about relaxation, we have to find a way to circumvent this theorem. And there are, okay, two possible ways. One is consider relaxation on average. So one just say that, well, if I just now pick a random time, but very large, then what I find is that there is a high probability that the state, the expectation value of my observables will have a particular value. It will be, for example, a thermal value. And otherwise, there is the possibility to take the thermodynamic limit. Because in the thermodynamic limit, what happens is that since the energies are proportional to the volume, while the number of states is exponentially large in the volume, then this means that the gap between the states will become zero, and then we can't apply anymore the theorem, the quantum recurrence theorem, because there is the assumption of discrete energy level. So, okay, now in this part of the talk, I would like to use an intermediate point of view. So I will consider time averages, which is generally what one does when follow this kind of study relaxation of finite systems. But I will study this time average in the limit of large system size. Why I want to do this? The reason is that if you construct this object, now this is the time average of the state in a given time window, then you realize that it gives you some information about the quantum space. In particular, okay, just to see what happens, let's imagine, for example, that the overlap between the state at different time, it can be either 0 or 1. This is very unphysical, but let's imagine this. Then you immediately see that this operator, the eigenvalues of this operator will give you the fraction of time in this time window that the state spent in a particular eigenstate of this operator. And moreover, okay, the number of this eigenvalue give you the size of the space which is visited by this non-equilibrium state. So in fact, okay, this never happens. In general, you have that this overlap is different from 0 and 1, is very close to 0. So the situation is different, but nevertheless, what we can say is that the state at any time is a linear combination of the eigenvectors of this time average density matrix. And moreover, we can also say that if we truncate now, if we yes, this operator removing the eigenvectors with the smallest eigenvalues, then this turns out to be a very good approximation of the time evolution. So we can truncate the space in this way. And so in the next slide, I will just compute how many states we have to keep in order to have an accuracy which is 1 minus epsilon for some given epsilon. Okay? So the first step is to compute what are called the Renier entropies, so I can compute the moments of this density matrix. Why it's convenient? Because if I compute all the moments of the density matrix for integer alpha, then I can immediately, okay, but I can deduce the distribution of the eigenvalues, the entire distribution. And this is related to the fact that the eigenvalues of the density matrix are between 0 and 1, so this is a well-defined problem, and there are no ambiguities in this. So once you know the integer values, then you know the distribution. So, okay, we have to compute this object, raise of rho bar to the alpha. And now you can imagine now that you have here many operators. Let's consider just in the middle of this, you will have two close by operators. And then you will see you have the integral over the times. And then you will see this overlap that appears here. Now, what is the behavior of this overlap? Well, if we write the time evolution operator explicitly, then what we find is that if these two times are small, then we can expand. And then this is nothing but the exponential of the cumulants, the energy cumulants times the times. It's a definition of the cumulants of the Hamiltonian. So it's clear that if we want to solve this problem, to find this number of eigenvalues, we have to know some properties of the cumulants in our particular systems. So the system we consider generally are described by Hamiltonian, which are local or quasi-local. And so, well, what do we know in this case? Well, we know that if we now prepare the initial state in the ground state of some quasi-local Hamiltonian, we have essentially two possibilities. Either the correlations decay to 0 exponentially, or generally there could be some kind of critical behavior, and then there are correlations that decay as a power laws. Yes.
When we expect.
Yes. How can you do this? You can just take the derivative. It's written here. So it's just this is the definition. Yeah.
Okay.
It's this the definition of the cumulant. So these are the two main possibilities. And so what one can prove, I thought it was easier, in fact, but it can be proved, but in a kind of a more complicated, way, that the cumulants in this case are proportional to the volume. Okay. Instead, in the other case, you can have some hyperscaling behavior, so they can have a different exponent, or you can have this kind of behavior. But okay, so far, let's just focus on this simple case, which is the generic case. This is what you expect for a generic system. So this just gives you the information that these cumulants are proportional to L to dd. This is the dimension of our lattice. They can be 1. So what can we do? Since this is exponentially decaying with the system size, then this means that only with the contribution from close by times count, because the rest is just gives 0 contribution. It's exponentially small in the system size. So we can expand and use the expansion that I showed you before in terms of cumulants. And then finally, we can also compute the asymptotic expansion, the limit of large L of this. So just to be clear, here the time is finite, fixed time, and then I consider the limit of large L. And this is what one finds, okay? So there is this term, and then from this, we can compute immediately the Renier entropies, and we see this behavior. So the Renier entropies grows as the logarithm of the volume, and then also as the logarithm of the time. At first, when I found this, I was a bit surprised because, okay, we are considering quantum quenches, so I'm used to see linear increase of the entropies. Instead, there is a logarithm t. This is because, okay, here we are considering the entropy of the entire state, time average state, is not the entropy of a subsystem. And nevertheless, it's kind of, you will see in a moment that it's kind of surprising. Because now if we compute, we use this result to compute the distribution of the eigenvalue, and then to see how many states we have to keep to have an accuracy epsilon. Okay, sorry, this is just to show that the prediction is correct. Okay. So, well, anyway. So if we do this, so if we compute the number of states that we need to keep in this time average density matrix, we realize that this is proportional to the square root of the volume and proportional to the time. And okay, there is an error function, the inverse error function that takes care of the fact that we are putting some accuracy. We want to be accurate at order epsilon. And this is a bit surprising because, okay, when in numerical simulation, in the MRG or whatever, generally you have an important parameter of the system is the entropy of alpha system, and this generally grows linearly in time. So this means that the number in principle, if you don't cut the space, so the number of states that you must consider is exponentially large in time. But here we see a result that it's just linear in time, which is a kind of, on one side, it's really surprising. The fact is that here, when I'm considering only the spectrum of this time average state, so what happens is that the states, the eigenstates, can be very complicated indeed. What I'm saying is that we can find this kind of basis that in which time evolution is very, very easy. But then the problem is to find the basis. Okay? And okay, just also to show how small is the space, let's consider the time evolution of some local observable. Then, because the Hamiltonian is quasi-local, then we know that there is a bound at which information can propagate, given by the Lieb-Robinson. And so this means that whatever large is the system, in practice, only the degrees of freedom that are close by to the support of the operator are important. And in particular, we can cut the system to some subsystem which, with an extent which should be equal to the support of the operator, plus twice this Lieb-Robinson velocity, and then plus, okay, there could be also some shift due to the correlation length in the initial state. But still, this is a finite value, and for large time, this is just proportional to the time. So in the end, if you want to simulate, yes, if you want the best simulation of the time evolution of a local operator, apparently only need a number of states just scale like t to the 3 alpha in 1D, for example. So it's not exponential in the time, but it's just a power law, which is kind of surprising. And why I'm telling you this today? Because I want to say, okay, that in fact, whatever we consider when we study this kind of time evolution, the system is always in a kind of very tiny part of the Hilbert space, which is a bit also against our common intuition when we say ergodic theorem, that so the state should go everywhere. In practice, it's not going everywhere. It's just in very tiny part. And then, okay, this, from my point of view, it could mean that, okay, it means that I don't need to know all the details of the state. I can describe the state using only a reduced number of fields of information. And this is in connection with what happened when we study local relaxation, for example. When we consider the limit of large time, we see that we can describe this very complicated time evolution just using some set of root densities, or even in a non-integrable model, we can just say that this is a Gibbs ensemble, which is a huge simplification. So, but okay, here I want to use a different, I want to infer something different. I want to say that maybe we can also find some invariant subspaces, so some subspaces that the state cannot live during time evolution. We already know some of these subspaces, and in particular, we know that the entropy of the entire state is conserved, so not only the entropy, all the eigenvalues of the density matrix, so is already the state cannot leave this kind of surface. What I argue here is that there are more of this kind of subspaces. And so the program is that I would like to write my time evolving state like through some fields, okay, that describe the state at any time. And then what I want to find is that if I can decouple the time evolution of different fields. Because if I can, then I can say, oh, now I consider the class of state with psi equals 0, and then they will be described only by this equation, and vice versa, okay? And okay, there is indeed a trivial example. Trivial example of the stationary state, for example. So if you start from a stationary state, it will remain stationary, the same state forever. And So let's start considering a stationary state for a translation invariant Hamiltonian. We can depict it in this way. So this is the position, this is the energy. Let's imagine to pick this stationary state. What I want to do is to try to imagine whether there exists this kind of invariant subspace if we deform a bit the stationary state in an homogeneous way. So I would like to do something like this. So to define some kind of state which now doesn't have a fixed energy. We have different energies, for example, in different positions. And I'm wondering whether when I study time evolution of this object, I don't know what is this now, it can be represented always in this way at any time. So I remember that many times when I was an undergraduate student, I saw this kind of picture. I could understand what could it mean, because I don't know what does it mean to have an energy on a position and a different energy on another position. So this is what I want to do to clarify how is that possible. Okay, how can you construct this kind of states? And then, okay, the other problem is that how can we, even if it exists, let's assume that this invariant subspace exists, how can we parameterize it? And because, okay, this is just a deformation of a stationary state, we start seeing how we generally parameterize stationary states. And in particular, I will consider integrable systems. So in integrable system, okay, you already had many lectures on that, also the previous one, so I will be very, very quick. I want to say, okay, generally, when I think of integral system, you can have in mind either free bosons or whatever, non-interacting systems, or interacting integrable systems. And so what is yeah, I just draw some parallel between the two. So you have for fermion system, for example, you have that you can label the state by the momenta of your particles, even for bosons, okay? Or here I call them lambda, you can call them rapidities if you want. And then whatever the state consists just of all the fermions, or a bunch of fermions here. Then if you want to compute the energy of the state, it's just the sum of the energy of all the particles. The same for the momentum, for the other charges, so nothing special. What about integrable system? Okay, now we have something actually very similar. So we can again label the state by means of rapidities. And now you see that here appear different operators that act on some vacuum. And this operator now have a non-trivial algebra because the system is interacting. Nevertheless, all these quantities here have the same structure. So again, all the energy, momentum, local charges can be written as a sum of some function of the rapidities. Okay? And in particular, okay, we can imagine to take the thermodynamic limit here. So when you consider a large L, then you have that this will be proportional to the body, to the length, and then you can replace the rapidities here, the sum of the rapidities, like with an integral, weighted with the density of the rapidities for given rapidity lambda. And the same you can do in this other in the interacting case. Why here you see that there is some sum over n or something else? Because, okay, as also Ben was explaining before, in interacting case, you can have several patterns. So it can happen that you can have bound states. So you must be able to somehow to isolate in the sum different contribution. Then you can take the thermodynamic limit. And then you can define this density of of particles also in the interacting case. So it's, you see it's very, very similar. And in both cases, you see indeed that everything apparently is described through the root densities, through this quantity. And okay, now there is also some difference about interacting system, and the difference is clear when one considers excitations. And in particular, in the interacting case, if you add an excitation, let's make this is just a state. This is a label. This is a representation of the fermions in the state. If I add the fermions, then all the other fermions don't care. I can remove a fermion, the other fermion don't move, don't care about that. I do the same in the interacting case. I add the fermions and all the other, fermion. I add an excitation, all the other rapidities shift. And this is related to the interaction. So this is the biggest difference between non-interacting and interacting system. Nevertheless, they both can be described in this limit by a set of functions, root densities. Okay, now that we have identified the functions, then the question is, can I now use this function to just lift them to a new level and say I want to put some dependence on the position, the root density, and maybe I can describe it. This will be the way to describe my invariant subspace. And then, okay, the second question: how is root density time evolve? And okay, now I want to just just indeed relate to what was done before. So I want to draw a parallel. What we indeed, we saw the emergence of GHD in a kind of effective description in the Euler scale, something that you can, somehow it means that you don't care about whether this invariant subspace exists. The idea is that if you consider a particular limit, even if the state is oscillating in this kind of, in the Hilbert space, and it includes all the possible states, so it's not invariant, but then because you are considering particular limits, you are unable to see the difference between different states. And then, okay, using this kind of point of view, then you just say that, okay, I'm humble, so I want to just, I want to describe the system in this limit. And then you obtain this kind of first order, okay, generalized hydrodynamics, which I like to call first order GHD, just because there is a first derivative. And this was, okay, discussed a lot in these 2 weeks. There is another point of view, which instead they say, okay, let's instead assume that this invariant subspace exists. Then I can imagine to pick a state in this invariant subspace, and then what will happen is that it will be described at any time exactly by this root density. And so in this picture, the GHD equation is just a Schrödinger equation. So it describes everything. It's just a way to rewrite the Schrödinger equation in this reduced in this invariant subspace. Okay, so there are problems here. There are a lot of problems. And first of all, if we want to construct this invariant subspace, we must have an unambiguous definition of the quantities, because otherwise it's impossible. So we have to understand what this space-dependent root density means, and what we have also to connect this root density to the expectation values of observables, which is what we generally do, or correlation, whatever. Then there is another problem, because if we want to prove that this is an invariant subspace, we have somehow to be able to keep under control also the rest. So we know that the other degrees of freedom won't enter in our dynamical equation. And moreover, it's not even clear what this invariant subspace contains, because it could be also true that these root densities are not enough. So this is a very minimal idea, so that we can describe everything by root density. Maybe we will have to introduce also other quantities. I don't know, so it's not clear. But okay, just to understand how to do that, let's consider a very simple example, okay? Let's consider this model. It's the XX model. I think that all of you know this model. It can be mapped to free fermions and by general linear transformation. And okay, this is the phase diagram of the model, so but it's not particularly important. What is important is that this model is invariant at U1, okay? So it commutes with SZ. And why is important? Because there is some very amazing property, is that if you consider a generic non-interacting operator, which is invariant under U1, then it commutes with the Hamiltonian, with any other U1 non-interacting operators. So immediately, without doing any calculation, we know the set of conservation laws for this model. Is any Hamiltonian you can imagine that there is U1 symmetric and non-interacting. How can we use this? Well, now let's write the conservation laws at the sum of, in this kind of extensive way, so sum of charge densities. And then we compute, we write also the currents here, like the commutator with the Hamiltonian, the charge densities. And what we can do, we can enforce easily that also the charge density could be 1. You can enforce the symmetry again. And what we find is that all the currents are conserved if we do this. Why I'm happy? I say that we solved the problem, because now imagine to construct this particular state. It's just a density matrix, so a linear combination of all the charge densities. Since the currents have the same structure here, I'm claiming that when you consider time evolution, it will remain of the same form. But now, okay, you will have some time dependence in this Lagrange multiplier or whatever. So, well, this is not, as also Ben was saying before, it's not a very good parameterization, so it would be better to write everything in terms of root density, but okay, I will do in a moment, consider a more general system. Because, okay, this is a very trivial case when indeed everything is conserved, so there is no particular surprise that one can do this. So let's consider a more generic non-interacting spin chain. And well, if you can write the Hamiltonian in this very general form. And the first, I think, to introduce it was Suzuki to write this kind of a generalized XY model. And an example is using Hamiltonian. And then, okay, you want to do the same. And then you try to construct the charges, and you don't have a U1 sim, but you want to construct everything. And what you realize that if you now try to define the charge densities in a local way, which is what we generally do, I think, when we try, then there is no way to make the total currents of the charges, which are all under reflection, to be conserved. So there is no way. So in this model, you can find they are not conserved. So immediately I want to say, okay, well, then there is a problem. Maybe I can't do that. In fact, we can. And the reason is that there is a quasi-local gauge. So we can change in a quasi-local way now the charge density in such a way that everything is conserved in this model. Okay, so also the currents will be conserved. And then I will show you now the result. Okay. And in particular, what we can do, because it's a non-interrupting system. So when I say system, I mean both state and Hamiltonian. So the state will be a Slater determinant, and we will evolve with the Hamiltonian that I showed you before. Then this means that you can write all the expectation values in terms of a two-point function of the fermions, the Jordan-Wigner fermions. And in particular, okay, it's very convenient to define this object, which I generally call symbol, which is a sort of Fourier transform of the correlation matrix, as you see. There is a Fourier transform. But now, because the system is inhomogeneous, then you see it's not really a Fourier transform, because there is still a dependence on the position in this kind of sum. And then, okay, there is also a part which I call the amphis, which has this property. Why I called it amphis? Because you can check immediately that if you just put any function here and then you go back to the correlation matrix, you realize that they don't affect the correlation. So it's completely free, this part. We can put whatever we want. And in particular, we'll use this freedom because I want to work with a smooth function, actually with integer function. So it will be, you can take whatever derivative, it will be smooth. Okay, so I just show you the result, and the result is that if you now parameterize this symbol in the following way, okay, then something happens. So first of all, I want to describe this expression. Now here is just, if you want, is the Bogoliubov angle. It's a generalization of the Bogoliubov angle. You can imagine that this term doesn't exist, so it's just a usual transformation, Bogoliubov transformation that you can have, for example, in Ising. And then you see, okay, that there is some weird part here, that the momentum is shifted by a derivative, okay, which acts on the right, and here the same, but which acts on the left. And here you can identify what is the root density, and in particular, this if you define the root density in this way, you see that in the homogeneous limit, the root density actually is what we call root density. It's just the expectation value of the mode occupation numbers in our system. And moreover, you have clearly there are also the additional degrees of freedom, because this is a quantum system, so there is not everything is not conserved. So we have to introduce an auxiliary field here that indeed in the homogeneous limit describes the off-diagonal matrix element of the density matrix. Now, this is just a parameterization. This is nothing but more than that. You can always do this. And now the interesting part comes when one studies time evolution. Because what happens? Well, what happens is that these degrees of freedom decoupled. Okay? So now you have two different time evolution dynamical equation, different form also. And this, okay, what you see here is called the Moyer-Star product. It's just a compact way to write this kind of a series of derivatives. And if you want, there are also maybe sometimes it's better to consider integral representation of it. So it's a well-defined product. And okay, if you're not familiar with this, maybe it's better if I show you the expansion in the limit of low inhomogeneity, and this is what you find. Okay. And here I show up to the 7th order here for all the year. In particular, you see that at the first order, you find what we know, first order GHT, which is a classical result. There is no H bar, so there is a classical time evolution. In order to see the first quantum effect, you must go to the third order. And this is what you find. And this is a very interesting part because it gives rise to KPZ universal behavior at the Lycon. So you can describe it just using this term. Then what about the other part? Well, the other field, you can see that it's essentially quantum. It's essentially quantum because because as long as this energy, the even part of the energy is non-zero, then you have that this oscillate rapidly in. So you see the limit. You can't take the limit h bar goes to 0 for this field. And okay, so this was for homogeneous Hamiltonians, but in fact we can also do the same for inhomogeneous Hamiltonians. Okay, because yes. Yeah, there is h bar. In the continuum, what do you mean? Yeah. Yes. No, well, no, it's not true because it's a considered free theory. In the continuum, you have the dispersion relation is square root of p squared plus m squared. Then you have all the derivatives up here. So you have the term. Okay. Yes, it's practically classical. Yes. I think it is what you find when you study harmonic oscillator. Or no, sorry, this building. Yes. In that case, yes. Okay, so this is for homogeneous Hamiltonian and inhomogeneous states. Now we can extend everything for inhomogeneous Hamiltonian. Now here it will be more complicated to see what the notation, I think. But anyway, this Hamiltonian is just a linear combination of is a quadratic form of Fermi. It's very generic, the most generic quadratic form you can imagine, parameterized in a convenient way. Then here you see again that I'm calling, okay, what is x here? Because I forgot to stress before. X is an integer number times lattice spacing, okay? But in all these expressions, you see there are derivatives with respect to x. So you can actually assume that x is a continuum variable. So you don't need to remain at integer values. What happens is that all these expressions are exact when you compute them at integer values. So, but you have actually, in the end, it's a continuum theory. You can imagine that your variable position is just a continuum, and it's real, and it works. Okay, here, okay, the symbol now, the Hamiltonian, is convenient to be parameterized in this way, in the most generic situation, which is a very terrible way to parameterize it. I mean, if you know, if you give me an inhomogeneous Hamiltonian, I probably wouldn't be able to do this. It's easier to do the opposite. So you could imagine to just decide to imagine to put some dispersion relation here and to invent some Bogoliubov transformation. Then you will be able you could see what does this mean in real space. But if you do that, then what happens is that and then you parameterize then the correlation matrix in this way, though where this I forgot to tell these are star exponential, which are is like the exponential, but where you replace all the product by star product. Then what you find is that, again, this quantity rho and psi decoupled, and they satisfy, again, the same equation. The only difference is that now you have in the dispersion relation depends on the position. And in particular, okay, I wrote here the first order. So you have here the standard hydrodynamic equation part. Then you have some correction, which is exactly what Ben was showing at the end of the lecture. In the interacting, actually, it's really the same expression in the non-interacting case. It doesn't change anything. I should say that the first time that I obtained this expression was a few years ago. I was a bit puzzled because if you think about that, when you study generalized hydrodynamics in interacting systems, then you realize that indeed all the energies, all the rest energy depend on the position. So if you want to find an analog in the non-interacting setup, I was thinking, well, the analog should be a non-interacting Hamiltonian, which now depends on the position. And so this would be the correct hydrodynamic equation. This is really surprising that this time instead, apparently. It's not present in GHT. This is something that puzzled me a lot. Anyway, so this is the summary of the talk. So I show you that time evolution after quantum quenches occurs generally in a tiny part of the Hilbert space. And then I show you that in the non-interacting spin chains, there are invariant subspaces which generalize stationary state, and we can also write a dynamical equation for the corresponding fields. Then, and in particular, I show that the generalized hydrodynamics is just a Schrödinger equation, so you can expand it any order. It's exact. It can be seen as an exact theory. So this is only non-interacting. So clearly there are questions like, can this picture be extended in the interacting case? And is there more of a criterion to identify the gauge, the particular gauge that works well, even if one doesn't know that this invariant space exists, or is there some way? And moreover, okay, the other question, the final question is, are the root density really enough in the interacting case? Maybe one can't really expect that the currents will be conserved, and then maybe there should be auxiliary fields in this case. And okay, with this, I thank you for your attention.
In the free case, you can describe everything with the Wigner function. No?
Okay, it's an interesting point. How do you define the Wigner function? And as far as I know, generally people did that you have a state, and you can define a Wigner function given the state. Okay. Here it's like any Wigner function. It's true also because it's clear that this is like the time evolution of the Wigner function. It's nothing more than that. So rho can be interpreted as a Wigner function. But what is important here is that rho depends on the Hamiltonian. It's not something you can define a priori on your state. This happens because you're lucky all in the XX model. But instead, here I'm just saying that it exists. Yeah, it exists a Wigner function that describes everything and describes time evolution in this space.
Yeah, but you still would have the field psi. So Wigner function would not be enough.
Of course, no, but this is known. So the Wigner function is not, even in the XX model, you have off-diagonal contribution. So they exist always. You can imagine that hydrodynamics describe everything. So there is always something which is oscillating. It's quantum. We are considering a quantum model. Yes, I don't know if this is known in the literature. It was shown, this kind of a question. This I have no idea.
Any other question? Comment? Okay, so thanks a lot again.
Okay.